Okay, so second talk in the session is called Disentanglement with Futures, State, and Interaction, and Stefan Muller will give the talk.
Jatin, unfortunately, was not able to make it to POPL this year, so you are stuck with me giving the talk. So before I get into the main bulk of it, what is disentanglement and why do we care? So functional programs are known for allocating memory at a very high rate, and this problem is only compounded when you add parallelism. So this makes it very difficult to efficiently manage memory, especially in a functional parallel program. So disentanglement comes to the rescue there. It's been shown over the course of a number of papers at various conferences that disentanglement allows us to efficiently manage memory in parallel programs. And in one sentence, disentanglement is the property that concurrent threads are oblivious to each other's allocations. So for example, if this tree on the left is our tree of spawning of threads, these two threads are in a parent-child relationship, so the thread on the bottom can see its parent's allocations, but these two threads are concurrent, so they cannot see each other's allocations if the program is disentangled. So it's been shown that disentanglement, this property, holds for all purely functional programs and also for programs with limited determinacy races. And I will say a bit later what I mean exactly by determinacy races. But this has only been shown in the context of nested parallelism or fork-join parallelism, which is much less general than something like futures, which Francis introduced previously, almost like we planned it. So as you've seen, futures are useful for implementing pipeline data structures. They're also useful for implementing interaction if you have interaction in your language. So one example we use in the paper is a web server where we spawn a new future to handle each client asynchronously. Then we periodically poll the list of futures to see which clients have completed. So that's one primitive we haven't seen previously. It just returns whether or not that future has completed. And then we can actually block on and get the result of the future using the get keyword. So this paper extends all of that theory for disentanglement to a language with futures. Why is this interesting or surprising? Well, futures appear, if you think about it, inherently entangled. So to show this, let me show a particular allocation trace of a program with futures. So I'm going to use the notation that A with a location and a value indicates an allocation of a value of a location storing that initial value. F with a location and a value indicates touching a future whose cell is stored at that location, getting back the value V in response. So let's say we have a main thread. It spawns a future A and then continues on the right as main. The first thing that the continuation of main does is allocate a new reference cell to store the future handle for A, or the future result. Let's say that A then spawns a future B. And again, allocates a location for that future cell. A then allocates another location, L double prime, which stores the result of the future A. And so this is what it returns back when main syncs on that future A. So main now has access to the location L double prime because it was returned by A, but these two threads look to be concurrent. So main should not be able to access even the returned result of the future A. That looks like it would cause entanglement. However, we note that if we just slightly change our viewpoint on what is concurrent, actually we shouldn't be considering main and A concurrent at all because A has already finished. So if we rewind a bit before A returns and look at it in this way, once A allocates its return value, we can actually rewrite the tree such that it now appears that all of A has happened before the continuation of main. This is okay because we know A is done. It has allocated and returned its return result. So now when main synchronizes with A and gets back the result, it's clear that this is no longer entangled. And we call that transformation the join transformation, and that's kind of the key insight that allows us to prove all of the rest of the results in the paper. So what do we prove in the paper? We show that pure functional programs with futures are entangled, now not just fork join parallelism. That remains true if you add I/O effects to the language. It also remains true if you add mutable state to the language, but you keep your program free of determinacy races. And again, I'm going to put off slightly what exactly I mean by that. That's still a fairly strong property for a program to hold. So we also relax it a bit in a way that I'll show. And the last result is a bit off the beaten path of the other results. So we show that disentangled programs with futures are deadlock free. So now if we introduce futures, you have the potential to have deadlocks, but we show that if you keep your program disentangled, you won't. So this actually slightly changes our view of disentanglement, which previously we've seen mostly as an efficiency property, but now you can actually view it as a safety property as well, because it's guaranteeing deadlock freedom. So this is the calculus that we use to prove most of the results. In the paper, we also have an intermediate language where we don't include references, but in the interest of time, I'll just jump to the more general result. So we define disentanglement over these action traces. So I've shown two of the actions already, the allocate action and the sync action. We also have actions to show that a location is read and an action to show that a location is mutably updated. We can concatenate action traces, and we can use the bullet to represent the empty action trace. So disentanglement is defined as a judgment over action traces, where this A context defines or specifies locations that were allocated by ancestors. So effectively, these are the locations that it is safe to access. So the inference rules for this judgment are fairly straightforward. They just enforce that all of your accesses target and only give access to locations that were in that set A, that are locations that you should intuitively know about because they were allocated by your ancestors. When we're checking a concatenated action trace for disentanglement, so T1 concatenated with T2, we check T1, and now the locations allocated by T1 become ancestors of T2. So we have to be careful to add those to the context. So that is for one sequential thread. So that's a sequential action trace. This generalizes to computation trees, where the definition of ancestor generalizes in the obvious way for the computation tree. So on the left, before we do this join transformation, the A thread all the way at the bottom on the right, the second allocation there, at that point, the only ancestor that we know about, or the only location allocated by an ancestor, is L prime. Otherwise, there are no locations allocated by ancestors. On the other hand, once we've done the join transformation, if we look at all the way at the bottom of the main thread, by the time we synchronize on that future A, we have access to L, L prime, and L double prime, because all of those have been allocated previously by ancestors. So finally now, I'm going to define what we mean by a determinacy race. So a determinacy race means two concurrent accesses to the same location, at least one of which is a write. So this is somewhat more restrictive than the standard notion of a data race. So here it matters, for example, not just that the result changes, which it might, but also just that there were even just two locations, two writes to the same location in parallel or concurrently. So our theorem in the paper is that if you, starting an initial configuration, run a program for n steps, where n could be any number of steps, so this is not necessarily running the program to completion. If all of those intermediate trees are determinacy race free, and again, this is a judgment that we define inductively over computation trees, then the nth tree, so wherever we stopped in that computation, is disentangled. So because we can set n to whatever we want and stop at any point in the computation, this in turn means that as long as all of the steps up to this point have been determinacy race free, then if we stop and take a snapshot of the computation tree at any point, that computation tree will be disentangled. So as an obvious corollary, if you run the program to completion, then the program at the end is still disentangled. So the intuition for this proof is that in order to get a pointer to a non-ancestor, which is how we would create entanglement, a concurrent thread has to write it somewhere we have access to. So let's show an example where that happens. So this main thread allocates a location L, initialized to null, and then spawns a future. The future allocates a location L prime and initializes it to V. Meanwhile, back in the main thread, we now have access to L in both threads. In the spawned future, we update L to be a reference to L prime. So now this leaks that location L prime into L. So because we have access to L in the main thread, we can read it and get access to L prime. This is entanglement because these two threads are concurrent, and so the main thread should not be able to have access to L prime, but now it does. The reason it does is that there was a determinacy race. So we have a race between the read and the update. So they are two concurrent accesses to L. One of them is an update. So that was a determinacy race that leads to entanglement. So now you might ask, our example here of how a determinacy race can lead to entanglement necessarily involved a determinacy race on a pointer in particular. So you might wonder, is it okay for there to be a determinacy race if the determinacy race doesn't share a pointer? And the answer is actually yes. So to show this, we do effectively some unboxing. So before we had all of the values were locations and anything else is immediately allocated in a heap cell. But now we allow certain classes of small values, which are also the primitive values of the calculus. So these are just Booleans and integers. Everything else is still stored in a heap cell. So we then define weak determinacy race freedom, which allows for determinacy races on small values, but not on locations. So the theorem is exactly the same as before, except that we replace determinacy race free with weak determinacy race free, and we still have the result that the program is disentangled. There's a cool application of this in the paper, which I don't unfortunately have time to go over. It uses compare and swap on Booleans and shows that this still won't result in entanglement. So we also don't include futures as small values. So in addition to pointers, if you have futures allowed to participate in determinacy races, you can create entanglement. You can also create something arguably worse, which is deadlock. So similar setup for this example. We allocate location L initialized to null in the main thread, spawn a future A. And then the main thread updates this shared location L with the pointer actually to the future itself. The future reads the location L, which now contains a pointer to its own future cell, which now allows, so this was a determinacy race, so indicating something bad is going to happen. It's also entanglement, and it allows A to synchronize on itself, which creates a deadlock. But we do show that if you don't have entanglement, then you do not create the conditions for deadlock. This is not inherently necessarily surprising. It's already fairly well known that data race-free programs and determinacy race-free programs can't lead to deadlock. But this shows that that is also true for the property of disentanglement, which we care about for efficiency reasons as well. So this theorem just parses as if the program evaluates and at every point it remains disentangled, then the program, and the second line is essentially just a statement of a relatively standard progress theorem, which in this case, the main way that the program would get stuck is deadlocking. So there's lots more in the paper. So I encourage you to take a look, and I'll be happy to take any questions.
Hi, thanks for the very clear talk. You didn't explain about the joint transformation. What are the implications on the runtime? Do you need to manipulate the region, merge regions, or change your stack of regions? How does it work?
That is a really good question that I am not the one to answer. So we don't have an implementation of this in, say, Maple, which is the next obvious point of future work. I believe Jatin has thought about it a bit, what would be required at runtime. It's outside the scope of the paper. It's something that I'm personally really, really interested in and want to see, and I know that there's been a lot of talk about doing that. But yeah, I'm not sure of the details.
We have a Discord question. Are there disentanglement systems that offer synchronization primitives such as barriers or locks?
Disentanglement for, so Sam is over there nodding. For barriers or locks, I guess the answer is yes. But
okay.
I haven't personally read those papers.
So I have a question. If you were to replace references with something like LVARs, so some kind of unification variable, would that put you back into this like pure functional program paradigm where basically everything would be disentangled?
I have not thought about that in the context of something like LVARs.
Well, because the determinacy race sort of becomes a no-op, right? Because the monotonicity of the updates.
Right.
At least
well, I guess
that's
what
the
is
theory,
that? Yeah,
right?
so I mean, if you are talking about monotonicity and the LVAR of type, like one of our small values, then you get it even with, that's our weak determinacy race result. But I'm not sure what it would mean to have like monotonicity properties on pointers. Maybe.
Well, it's functional programming, so you don't have pointers.
So yeah, maybe there's an interesting way to make that add expressivity, but in all the cases I can think of at the moment, I think it's sort of subsumed by what we already do.
Are there any other?
Thank you. Very interesting. In the two theorems that you are showing us, you require that all the intermediate, I don't know what you are calling them, these trees of activations, you require that all of them are disentangled. And I was wondering, can you not weaken it? Cannot you not just require that the last one was disentangled? Can you go from an entangled to the disentangled and then lose the good properties that you want?
So what we require is that all of the intermediate trees are race-free, and then show that all of the intermediate trees are disentangled. Or is the question that could we just say that the end result is disentangled, and then is that all we care about?
The question is, if the last one has got the good property, do you then get what you want, data race free and deadlock free and so on? Does it matter that you arrived to a good one, and in arriving so you went through a bad one?
Okay, so you mean this theorem in particular, that all of the intermediate states are disentangled?
Yeah.
Yeah, no, I think that's important because especially with the join transformation, you could lose information about things happening concurrently that then might have created a bad situation that will cause problems later. I don't have an example off the top of my head, but it does seem like that situation could happen.
Well, thank you.